Hi, and welcome back to episode 14 of Polishing This Turd, where we go through and completely over the top modify and overhaul this SIEG 7x12 mini-lathe. When I left you last week, we'd finished fitting the tapered gibs to the saddle, so now the saddle and the cross slide are finished. So I thought this week it'd be good to start looking at some motion control. This is the original cross slide mechanism from SIEG. I had already removed this from the lathe when I did the T-slotted cross slide because I increased the cross slide travel and this was then too short. Things I didn't really like about it was this use of a set screw by the ball handle. This is already a rounded set screw. I think the original was just a normal cylindrical headed set screw where you keep whacking your knuckles on the screw as you wound it. This was already a product improvement. The second thing that was not really that impressive is that there's no bearing in here. It just runs metal on metal. There was a piece of sheet metal in here, sort of spring steel, to provide a little bit of artificial feel so you could zero your dials. Didn't work that well, I didn't think. This is also, although it's a metric lathe, it's got an imperial cross slide lead screw. So it's good by lead screw. As I always plan to CNC this machine, I bought this little ball screw. It's a 3/8 inch American imperial threaded ball screw. Unfortunately, it's only a rolled ball screw and it does have a bit of backlash. I made a shaft extension for it and also made up an aluminium nut carrier. Although I milled out the saddle slot as far as it would go, unfortunately I still can't quite bring the screw onto center line. So you can see it doesn't matter which way you align this, you can't get the screw parallel. Obviously I could do something like mill out a bit of this clearance hole here to bring up this end. But really there's not a lot of meat there as it is. Unfortunately, I have never been able to mount this screw. I did check out eBay looking for little 8mm miniature ball screws, hoping to find a ground ball screw for this axis, but all of them have flanged nuts, and most of the nuts are at least 20mm diameter. You occasionally find them some at 18, but even at 18 they're not going to fit under that cross slide, and I'd have to cut the flange off and find some other way of mounting them, so really the ball screw is not an option, unfortunately. There are other potential solutions like taking the ball screw out from the center of the saddle and placing it beside the cross slide, but I really don't like those solutions. One of the advantages of a lathe is they generally cut in one direction, most things being cutting from the outside, of course. Yes, you do have to take up backlash in the opposite direction if you then switch to a boring bar, but it's not that common that you actually cut both in the positive direction and in the negative direction on a single pass. Maybe sometimes when you're doing things like a chest pawn or something, you may be cutting in both directions, but backlash is not as much of an issue on a lathe as it is on a mill, so I think I'll just live with it. So this is the cross-slide drive mechanism I've been using for the last few years. The screw is a metric trapezoid 10mm with 3mm pitch. It's a left-hand thread, not really important for CNC because the machine doesn't care, but I figured since it doesn't care, if I put the correct pitch on there, if I do ever need to manually machine something while turning the knobs, at least I'll turn in the right direction. I originally tried using the two nuts in a sort of a spring-loaded anti-backlash sort of setup, but it's also small, there was no real space for it. I ended up just brazing the two of them together and using them as one large nut. You can see I've needed a little shim to space the height of the nut correctly. That'll have to be re-shimmed now that I've changed the height of the cross slide through scraping. I increased the length of the standoff because I've got greater travel with the cross slide, and made a bearing block with a pair of effectively skateboard bearings. Those should probably be replaced with angular contact bearings to remove all of the backlash, but then again there's always going to be a bit of backlash in this nut. The drive is just a normal standard NEMA 23 stepper motor with a plate with oblong slot to give a little bit of belt tension adjustment. This mounts across here. The drive itself is a 3-to-1 reduction with a little HTD belt. And then there's a cover for it to keep all the swarf out of the belt drive. I played around engraving this cover. There's a video, I'll attach it up in the corner. So first up I'll mount the nut. Now I'm assuming that it will need shimming, but I'm leaving the old shim out for now because it's unlikely to still be the same correct thickness. I've lowered the saddle, I've lowered the cross slide due to the scraping done. So the assumption would be that I need either a thinner shim or maybe to take a little bit of material off the top of the cross slide nut. But for now I'll just leave it loose. Next up we mount the standoff. This was made with quite deep screw holes. And then we can screw in the lead screw. Once again, all of these parts were made on the lathe for itself. Watch the end of the lead screw as we tighten the nuts mount screws. See how it deflects over towards the front? It doesn't really matter which one I tighten. Both of them will deflect it towards the front. That would be normal. Through scraping both the flatways and the V-ways, I've taken material from this side, which is the fixed way, and then I added material back on in the form of a new fitting gib strip. So the whole cross slide has moved towards the tailstock through the scraping, and these holes are now offset from the screw center line. So really I'm going to have to enlarge or overlace those holes towards the front of the towards the headstock to enable them to align with the screw again. Well, it just took a couple of licks with this rat's tail file to move those holes over enough to take the force off the lead screw. Next up we can mount the motor mount plate. I designed this around a specific belt length. The motor mount holes and also the central cutout here all allow about 2 millimeters of travel for belt tensioning. There's a spacer which goes on to ensure that the clamping loads on this pulley actually go through into the bearings to preload the bearings. There's a flat there and a set screw to align with the flat. And that's the finished cross-slide drive mechanism. Well, that was the X-axis, or cross-slide. Now let's look at the Z-axis, or the lead screw as you'd normally call it. In this case, I've got a rolled ball screw. It's not a terribly high quality item. There is a bit of play in it. It was just what I could afford at the time. You know, I've already made up all the bearing blocks and that for it, so that's what I'm going to use again. Now also heading to the scrap bin are the original Z-axis lead screw, which is shorter than it should be because I've been using it as scrap metal for the last few years. Here are the half nuts that go with it. The lead screw nut is mounted in this carrier block. The carrier block is this weird shape to allow the cover to come down over here and keep all the swarf off the lead screw. It then gets picked up by this replacement saddle. The saddle drive gears can go in the scrap bin. Not sure where the saddle went. I think I might have melted that down already. One of the nice things about CNCs is you don't need a very complicated hardware. You know, you don't need any lubrication or anything on the saddle itself. You probably should lubricate the ball nut, but I just tend to go in there with whey oil and lubricate it regularly. It's not rusted, it's never corroded. Go and keep it clean that way. Once again, we've got a NEMA 23 motor to drive it. This one's a bit stronger. I think it's a 3 amp motor. The cross slide's only a 1.5 or 1.6 amp motor. These parts, the same as the carrier parts here, were made by a couple of friends of mine years ago. The three of us, one in Belgium, one in Austria, and one in the United States, sort of together designed these parts. I did most of the design work, and the other two guys already had CNC mills, so they went in and milled the parts for me, which was really appreciated. Change gears can go in the scrap bin. And there we have it. That's the Z-axis lead screw mechanism. Let's quickly install that, shall we, and see how it goes together. I made this end slotted so that the length of this ball screw is not critical. Once again, this bearing block's got a pair of deep groove ball bearings in a sort of a preloaded configuration with this nut performing the preload. Same sort of thing I did on the cross slide. That was silly. So next up we mount the saddle to the ball nut carrier. Once again, the motor mount's got a bit of adjustment in it to allow for belt tensioning. It doesn't need much, it only needs about 1 or 2 millimeters of adjustment. So as you can see, there's my belt adjustment length there. Pulley goes on, I can't remember which way. Belt, and then the cap mounts, and you adjust the tension with those two. While trial fitting everything, I've actually found that this guard no longer fits. Unfortunately, this flange length here is too short, so I'm getting, as you can see this line here, I'm getting the gib adjustment screw scraping on the sheet metal. I tried bending that down, but then of course we get into a problem down here with the ball nut. So what I'll do is I'll make up a new one of these. Lurking under the table here is a little bend brake I made a few years ago. Bit of a funny story around this ruler. Years ago, I bought a pretty worn out Stratocaster that needed refretting. You can buy fret rulers, which basically just have gashes cut out at each fret position. I figured it would be easy just to make my own, so I bought this ruler from a hardware store, meter long, lopped off a piece and then used the angle grinder just to gash where I needed to, leaving this piece left over, which I've been using as a ruler ever since. And it was only after the fact that I realized, you know, if you're going to cut a piece off a ruler, the smart thing to do would be cut it off the long end rather than the zero end. But oh well, I guess I wasn't smart enough to think that through before I chopped it. If you think it's bad form that I use my dual table as a bit of an anvil at times, it is, and I'm sorry. But one thing you do need to know is dual made tables with two different kinds of mounts. This one is a single swiveling mount, and as you can see, it's a very massive cast mounting structure underneath the table. A lot of the duals have a dual tilting mount, so it can tilt both in this direction and in the second direction. They're much lighter in construction, and they're really not capable of any sort of impact like I've just been doing. If you're going to use your dual as an anvil, make sure you've got one with a single tilting table. If you're wondering why I'm cutting sheet metal by hand rather than using the dual, it's because currently the insides of the gearbox of the dual are here in two ice cream containers. I'm not sure if you know how a dual works, but they have an input shaft and an output shaft with an intershaft bearing, or an intershaft bushing, I guess in this case. And unfortunately in my case, that is what Gwen from Blondie Hex calls chowdered. In fact, it got so bad that the woodruff key here leapt out and got stuck between this tooth and its partner, chipping it. I've contacted Dual to get a replacement of this shaft with its 11 DP 11 tooth gear, but unfortunately they want something like $1,500 just for the shaft. So yeah, that's really beyond my means at the moment. It's obviously been repaired a couple of times. There's evidence that there's been weld build up in the past in this area. Also, this has been welded up before. It's had a new slot milled in probably. For my usage, there's probably enough meat left in that one tooth, in that segment of tooth, which is nearly a third of the width, where it would probably work fine for the rest of my life. When you consider that duals were designed for cutting up to, 300 millimeters or 12-inch steel blocks, band cutting them before the days of wire EDM, that's something I will never do. So I have been intending to repair it and put it back together and just accept that the load-bearing capacity is much reduced due to this one tooth. However, what I've found is that the centers are no longer concentric with the bearing journals. So I have tried putting this on the Clarkson and using the Clarkson as a cylindrical grinder with this between centers to try and regrind this interstage bearing journal back to round. I guess what I'm going to need to do is regrind these centers back cylindrical to the journals before it can do anything. I have tried it, putting this in a 4-jaw chuck and bumping it around to try and get these running perfectly, and then use a little Dremel tool or something to re-grind those centers, but haven't got it perfect yet. So until I can get that working again properly, the gearbox of the dual at the moment is just bypassed. I made up a shaft, one-to-one shaft, where the input goes straight through to the output, which is basically the same as its normal high-speed gear ratio. Yeah, until I've got the low-speed gear ratio working, I can't cut ferrous metals. You'll be happy to know that I didn't bash this whole piece flat. on the Dewall's bed. I did it on my welding table. Have I talked about these before? Clecos, or Cleco pliers and Cleco clamps. Fantastic piece of technology. Came out of the aviation industry. Were used for sheet metal work a lot. This bender I made in accordance with a set of plans I found on some Australian, I think, woodworking website. I'll put a link down in the comments section to my build log, which I had on CNC Zone, I think is where I put a build log of building this. It was made mostly with pretty simple tools, a lot of time. And I did use that little, the little decal as a mill to mill out these shapes around through here. As you can see, it's a finger brake, so by taking off fingers and rearranging them I can also make boxes. It's got a drop down apron, so you can use it to do setback and bend allowance. Yeah. Unfortunately it's not that rigid, so you probably notice here that there'll be a difference in radius between the end and the center on this piece. Had a couple of dents in the first bend just because segments were not quite flush with their mates. So I'll correct that. That should be better. Next up, I'm going to dimple those holes. I don't have a lot of space between the tapered gib and the heads of any screws along here, so I want to use countersunk screws. Now, my dimpling pliers are aircraft parts, got from Aircraft Spruce a few years ago. Lovely, lovely tool, beautifully made. The dies are, of course, 100-degree dimples, as you use in aviation. Here I'm using 90-degree metric fasteners, so it's not a perfect match, but it'll still work better than having some sort of proud head screws there. This is just mild steel sheet. It dimples quite nicely, cold. Well, there's the new swarf guard installed. That of course means that the old one can take its place in the scrap bin. I think that covers enough for this week's episode. So once again, thanks very much for watching and look forward to seeing you in episode 15.